Everybody, welcome back. Um, Wanted to do a video just kind of on maybe the differences between chapter 5 and 17, um, and also just show you guys this decision tree here that might be able to help you think through these problems that you'll see in chapter 5 and 17, and also on the test 2, which covers chapter 5 and 17. And this will hopefully help you kind of decide, right? Am I kind of working on a chapter 5 problem um, where we're just taking calculating a probability under the curve for a population, or are we doing that for a sampling distribution? So if we start at the top of our decision tree, we want to ask ourselves, do you take a sample size of greater than 1? And so we've seen in a lot of these problems, right? These problems are a little bit longer word problems almost. Maybe a few sentences, almost a paragraph long. And we have to be able to pull the information we need out of the question itself, but we also need to obviously understand what the question is asking us, right? So this first question we can kind of ask ourselves and look for in the question, or the problem that we're working on can help us. It says, do you take a sample size of greater than 1? If the answer to that is no, then you're coming over here to the left side of this decision tree, right? And you're talking about a population distribution. So if you're asked for, what is the probability that, a monkey in your zoo lives less than 20 years, or what's the probability that, one person selected has a IQ score of greater than 120, right? If you're only taking a sample of size 1, if you're only asked about, one of your who's, right, from chapter 1, then you're just pulling that one person straight from the population that you are also given in that problem, right? Um, if you just so happen to be told that the population that one sample is coming from has a mean of 0 and a standard deviation of 1, then you're already in the standard normal curve, right? You're already kind of in terms of z-scores, so there's really no conversion that you have to do, right? You can take the value that they give you, just look for that in the z-table or plug it into the calculator with a mean of 0, standard deviation of 1, and you are good to go. But if not, right, which is usually the case, if you're given any other mean and standard deviation and you're asked to find the area under the curve less than, greater than, or in between some x value or maybe 2x values, then we need to calculate our z-score, right, for this population distribution. And the way we do this, right, is we take that x value that we're asked about, we subtract it from the population mean that we are given, right, or told about, that comes from our population distribution. And then we just divide by that population standard deviation, right? And those are the only two cases really for the population distribution. I don't think we've really seen a problem like this where we just start off in a standard normal curve. We pretty much always, have to convert the population distribution we're starting with to a z-score, right, to then find the area under the curve. So if we go back to the top of this, since we've handled the entire left side of this decision tree, if we go back and we ask ourselves again, do you take a sample size of greater than 1? If the answer to that is yes, right? If our question or our problem at hand is asking us, what's the probability that an average of 4 people have an IQ score greater than or equal to 120? Well, if the average of 4 people, right, that sample size is greater than 1, right? There's 4 people instead of just 1. So let's start there with that sample size. That sample size is greater than 1, so we say yes. So we're talking about a sampling distribution. Excuse me. And then the question, that same question said, what's the probability that 4 people would have an average or a mean IQ score greater than 120? So it's asking about the mean or the average of that sample, right? So we know we're in terms of our X bar, our sample mean. So we're talking about a sampling distribution of the sample mean. And we know that if we could take every single sample from the population that we start with, and with each of those samples taken, calculate the sample mean, then the average, right, of all of those sample means would be the same as our starting population's average, which we are normally given in our problem. And we know that the standard deviation of all of those sample means is equal to the population standard deviation that we're again given, and just divided by the square root of n. Right, so when we go to calculate this z value, now we're asked about one specific sample mean out of the distribution of all of our sample means, right? So instead of being interested in one specific x value, we're now interested in one of those specific sample means, right, out of all the possible sample means. And we just, again, can subtract the population mean from that because that is equal to the mean of all of our sample means. And we divide by the standard deviation of all those sample means, which is that population standard deviation divided by the square root of n. And then over here, so let's say that question was worded a little bit differently. Maybe it's a new problem entirely. And we're asked, what's the probability that a sample has that, 0.75 of your sample has green eyes, right? So that 0.75, right, is a proportion. Having green eyes also, right, is a categorical variable. So a proportion is going to always be about a categorical variable, right? You can either have green eyes, yes, or you don't, right? You could have green eyes, blue eyes, you could have hazel brown eyes, right? There's some finite number of categories that you can put that variable of eye color into, right? So when we're asked about those proportions of categorical variables, we know we're talking about proportions of our sample. Oftentimes, right, the question should just state it, right? What's the probability that the proportion of your sample that has green eyes is 0.75. So we're talking in terms of p hats, right? Sample proportions. Talking about a sampling distribution of our sample proportions. And again, if we could take every single sample possible from that starting population, calculate the sample proportion for each one of those samples, the average of all of those sample proportions would be equal to the population proportion, which we are given in our problems. And the standard deviation of all those sample proportions is equal to the square root of p, right? Again, our population proportion times 1 minus our population proportion divided by the square root, divided by n, and all of that is under a square root, right? So our z value here, we're going to be asked about, one specific sample proportion, right? What's the probability that a sample of, 10 people have a proportion of 0.75, right? So we're asked about that one specific sample proportion. We subtract that from the average of all those sample proportions, which is our population proportion. And we divide that by the standard deviation of the sample proportions, which is our p 1 minus p over the sample size. Let me take our square root of that. So hopefully walking through this kind of helps you decipher when you're working on homework problems or test problems when you're talking about a population distribution versus a sampling distribution.